Hello everyone. In this video, I will introduce SCE-Depth, a spherical compound eye framework for wide field of view depth estimation. Our goal is to combine bio-inspired spherical sensing with spherical neural processing to improve depth perception over a wide field of view. SCE-Depth has two central ideas. First, it processes compound eye images natively on the sphere, instead of forcing them into a planar representation. Second, it exploits a depth-sensitive gradient feature produced by overlapping ommatidia. The motivation comes from modality misalignment. Robots, drones, and AR systems need compact wide field of view depth perception. A common solution is fisheye imaging. However, fisheye projection maps spherical geometry onto a plane and introduces strong barrel distortion, especially near peripheral regions. Planar CNN models and transformer models then learn from a representation that is misaligned with the sensor. Our goal is to align the imaging geometry, the network representation, and the learning objective on the sphere. Our first key idea is native spherical sensing. The SCE camera is inspired by biological apposition eyes. Ommatidia are arranged on a hemispherical surface, and each one contains a lens and a single pixel photosensor with optical isolation. Each ommatidium integrates light within its own field of view into one intensity value. Collecting all ommatidial responses forms a hemispherical image. The second key idea is a depth-sensitive gradient feature. When the ommatidial field of view, alpha, is larger than the angular spacing, beta, adjacent ommatidia observe overlapping regions. Around object edges, this overlap changes the intensity difference between neighboring ommatidia. As depth increases, the inter-ommatidial intensity difference, denoted delta I of d, decreases. This provides a depth cue that is specific to the SCE imaging geometry. Any pair of SCE ommatidia with overlapping fields of view can be treated as a single pixel stereo pair. Each ommatidium outputs one scalar intensity value, so conventional stereo disparity is replaced by the intensity difference between neighboring ommatidia, which we use as a depth cue. Because many neighboring pairs overlap across the SCE, the system behaves like a multi-view camera with adjustable baselines. In the figure on the right, two adjacent ommatidia observe a bright to dark step edge. Let theta sub I of d denote the signed edge offset at depth d. The corresponding intensity is I sub I of d, and the inter-ommatidial gradient is delta I of d. According to equation 3, the relative viewing angle consists of a constant beta term and a depth-dependent delta of d term. Equation 5 then shows that delta I of d decreases as depth increases. We validate this cue in both simulation and a physical prototype. In simulation, as the target moves from 1 meter to 2 meters, the SCE edge response becomes more blurred and the intensity difference decreases. By contrast, the fisheye edge response remains nearly depth-independent. We also built a 37 ommatidia prototype, and the real measurements show the same decreasing intensity difference trend. This supports the physical basis of the depth-sensitive gradient feature. Based on this observation, we designed the SCE-Depth framework. The input SCE image is processed on the HealPix sphere. SGFE, the spherical gradient feature extractor, extracts gradient-enhanced spherical features and feeds them together with the raw input into a spherical network. During training, SGL, the spherical gradient loss, enforces consistency between the gradients of the predicted depth and the ground truth depth. Here we visualize what SGFE captures. For SCE gradient maps, the boundary response clearly weakens as the chair moves farther away. For fisheye images, applying the same Sobel-style operator does not show comparable depth-related variation. This confirms that SGFE is extracting a cue caused by the SCE imaging geometry, rather than a generic filtering artifact. For evaluation, we build compound depth using IsaacSim. Each SCE image aggregates responses from 20,609 ommatidia, and the dataset contains 5,456 spherical image depth samples. We also render paired fisheye data under identical scenes, so the comparison between SCE and fisheye modalities is controlled. We first study the design choices. The ommatidial field of view controls a trade-off between depth sensitivity and image clarity. The best setting is alpha equals 3 degrees, which provides enough overlap without excessive blur. We also compare several gradient operators and find that Sobel gives the best overall performance, so it is used as the default SGFE operator. The main quantitative results show that SCE-Depth achieves the best depth accuracy. On compound depth with alpha equal to 3 degrees, our MSE decreases from 0.350 for HealSwin to 0.256 for our method. On fisheye depth, our method also achieves the best RMSE and the best delta 1 and delta 2 metrics among the compared methods. These results show that spherical sensing and gradient-aware learning are both beneficial for wide field of view depth estimation. The qualitative results show the same trend visually. Compared with heel swin and SU former, SCE-Depth better preserves object boundaries, shapes, and fine details. The improvement is especially visible around edges and local structures, where the depth-sensitive gradient Q provides additional supervision for more accurate depth recovery. A key advantage of SCE-Depth is omnidirectional consistency. Fisheye-based predictions tend to accumulate larger errors near the periphery because the planar projection is heavily distorted there. In contrast, SCE captures the scene directly on the sphere, and the network processes it on heel picks. This leads to more uniform errors across viewing directions and better peripheral depth estimation. We also evaluate generalization and ablation. On SIN Woodscape and Stanford 2D 3D, SCE-Depth achieves consistent RMSE improvements over spherical baselines, showing that the design generalizes beyond compound depth. The ablation confirms that each component contributes. Native SCE imaging improves over the fisheye to sphere baseline. Adding SGL further enhances gradient level consistency, and including SGFE gives the best final result. To conclude, SCE-Depth is a bio-inspired framework for wide FOV depth estimation. It processes spherical compound eye images natively, avoids planar projection distortion, exploits depth-sensitive interommatidial gradients via SGFE and SGL, and improves accuracy and peripheral consistency. Thank you for watching, and please visit the code and dataset page for more details.